Computers in data centers are frequently reallocated from one purpose to another, or need to have their software updated, or need to be returned to some kind of known clean state. And this is particularly true in multi-tenant data centers. And one of the key tools for doing this is disk imaging. And so today I'm going to talk about a study that we did on the Emulab multi-tenant data center, where we looked at our production disk imaging system with an eye toward the operations and ideas for future research and design of disk imaging systems. So just a quick bit of background, what I'm talking about in disk imaging systems. So I'm specifically referring to taking block level snapshots of the contents of a disk, building up some library of these that is going to represent multiple, say multiple Linux distributions, multiple standard software installs, multiple versions of Windows, etc. And then when the needs in the data center changes, such as a different set of tenants comes in, or some tenant scales out their application, or some large-scale software upgrade needs to be performed, distributing the contents of one of these images over the network and actually installing it, writing it to locally attached disk on a set of target servers. So the disk imaging process is part of the provisioning process for physical and virtual machines. So it's kind of it's a critical piece of how quickly things can be re-provisioned in the data center. And it also can consume a lot of resources in the data center, such as storage, network bandwidth, etc. And so the properties of disk images and their usage have consequences for the way that we store these images, for whether or not we can cache them in different levels of the storage hierarchy, whether it makes sense to preload them in anticipation of future requests, and also their distribution over the network. So in this study, we look at a number of questions that help us understand disk imaging better. I'm going to talk about 3 of them in the talk today. There's more of them in the paper. So one of these is, what does the working set look like? So if we were to look at the popularity of images, how many we use in a typical day, et cetera, what does that look like? What do the images themselves look like at a block level? And what are the key factors that govern whether it makes sense to start preloading these images onto disks in anticipation of requests? So the data set that we looked at was, in the Emulab network testbed, which is widely used in this community and a few others, we, for the period of about 4 years, we logged every single request that we got to provision a virtual or physical machine, which over this time period was about 250,000 of them. And this represents a data set of about 1,300 users who belong to about 360 organizations, and about 700 unique images we see during that time. So Emulab is what you might consider like a small to medium scale kind of data center. So it currently has about 600 physical PCs in it. And the disk imaging model that it uses is this facility user image model, where the facility itself provides a set of standard disk images with popular Linux distributions, various versions of Windows, et cetera. In many cases, users come and they customize those base images, make some changes to them, and then they create their own snapshots. And the facility images are public. Anyone can use them. The user images can be made public, but typically they're used only by the organization that created them. So we'll start by looking at user behavior. And before we really start getting into this, I want to give a caveat. So this is a quote from one of the reviews of our paper. This person, by the way, admitted to being one of these odd beasts in the review. So, of course, every data center is going to be a little bit different. We don't have any data really that tells us how well the Emulab usage matches the usage of that you would see in other data centers. But at this point, this is the public data set that exists. And so, in order to kind of drive this forward, this is what we're able to study. And what we did is we tried to learn lessons involved that look at trends and so forth. So even if some of the details are different, we expect that many of the shape of these analyses are going to be similar. And this, I think the methodology that we use to analyze this could potentially be used to analyze other data sets from other types of facilities. So let's start by looking at a very basic statistic, which is how many of those requests are for images that the facility provides versus that the users created themselves. And you can see it's relatively balanced with about 55% of those requests being for facility images. And it's kind of interesting to look at the behavior of the heaviest users. So what we're seeing on this graph is each of those bars represents one organization, one of those 370 organizations, and these are all of them that requested at least 1,000 disk loads over that 4-year period. And so the part of the bar above the center line in blue is showing requests for facility images that user made, and the part of the bar below the line in red is showing requests that they made for images that they created themselves. And there's a couple interesting things to notice here. So first of all, most heavy users stick to either their own images or the facility images. They tend to not mix and match between the two a lot. And the heaviest users, the ones on the left-hand side, tend to use their own images quite a lot. So so this is so like the first, like in the top 15 users, most of them are using primarily their own images. So let's look at the popularity distribution of those images. So what we're going to look at here is on the y-axis we have a log scale number of requests for a particular image, and on the x-axis we sort the images by their popularity rank. And if we look at the facility images, so we have about 100 facility images in our data set, and they have a popularity distribution that falls off pretty quickly. If we look at the user images, what we have is a distribution that has a much longer tail. It goes out to, there were 600 user images in the data set that we looked at. And if you compare this to the exponential distribution, which is the dotted line that I just added, which in log scale looks straight, what you can see is that the facility images follow an exponential curve pretty closely. And what this means is that there are a relatively small number of extremely popular images, and the popularity falls off quickly. And if we look at the user images, they have a much more heavy tail distribution. So if we're looking at, it takes a larger number of user images to satisfy an equivalent number of requests for loading. So the facility images here have a smaller, lighter tail, which means that at several other points in our analysis, we're actually going to treat these two types of images differently. And the most popular image in this data set was fewer than 13% of all requests. So there isn't an image here that dominates usage. So let's look at what this looks like as the size of the facility scale. So of course we can't make Emulab any bigger, but what we can do is we can subsample the user base to see what it would look like, see what the trends look like as the user base grows. So across the x-axis we have percentage of the user base, where the right side is the entire Emulab user base, and as we go to the left we have a smaller random subsample. The number of user images that are used as the user base grows roughly linearly, which is maybe perhaps not surprising because these images are created by users for their own organization. So the more users we have, the more activity we're going to have along those lines. The facility images follow a very different curve. So here, remember that we only had roughly 100 facility images, and even at about 10% of our user base, essentially all of those get used. So the key here is that the facility images are in large part a property of the facility itself and not a property of the user base, right? There are only so many popular Linux distributions, for example. And so what happens is as the user base grows, if you just look at the total number of images, that very quickly gets dominated by user-created images. And the number of facility images is actually rather small. So let's look at the daily working set size. So we're looking at a histogram here where for every 1 day period over those 4 years, we looked at how many images were used during that day, and this distribution follows a pretty standard normal curve with a median of 12 images used per day. And remember that we had over 700 images in the full set, so the working set in a particular day is a very small fraction of the total set, which suggests that we have very good temporal locality, and if we want to do caching of images in different layers of the storage tier, there's some good potential here. And again, let's look at scaling as the user base grows, this time of that size of that working set. So here, as we increase the number of users, we end up with a daily working set size of user images that scales roughly linearly, which is in keeping with the total number of user images. But here, the facility images, the working set size actually also grows linearly. And throughout the whole ratio, throughout the whole graph stays roughly in that 55-45 ratio. But of course, remember that there are only so many facility images. So if we had a facility that was orders of magnitude larger than Emulab, this facility image curve is likely to max out at some point. And so what this implies is that as you scale to a very, very large facility, what you're likely to end up with is a daily working set that includes most or all of the facility-provided images, which are very popular, and then a very large, diverse set of user-provided images. So let's switch to looking at the contents of the images themselves. So we use a definition of block-level similarity that looks like this. So we have a base image that has some set of files already written to it. And to create a derived image, what a user does is instantiates a copy of that base image and then makes some changes to it, installs some packages, upgrades stuff, installs their own software, installs datasets. And then what we look at as the difference between these images is the percentage or number of disk blocks such that if I already had that base image installed on a disk, how many blocks would need to be written to transform it into the derived image. And the reason that we use this metric in particular is that previous work has shown that you can tune a disk imaging system such that the bottleneck is the write speed on the target disk. So if we're looking at kind of how quickly we can transform a base image into a derived image, the number of writes that we need to do kind of is a pretty good proxy for that difference. So here, looking at the actual similarity in our data set, here the derived images are going to be user images, and the base images are going to be the facility images that have the highest block level similarity with that derived image. So Emulab doesn't actually record the provenance of user images, so we have to use this heuristic. We assume that the most similar facility image is the one that a user started with. So this histogram shows that we actually have a lot of images that have quite a lot of similarity with their base. So we have a lot of images up in the 60-70% range of similarity, which implies a couple things. First of all, that putting these images in deduplicating storage is a very attractive option because there is so much similarity that we'd likely save a lot of space, and this is in line with earlier studies that have been done on virtual machine images. And this also suggests that the idea of differential loading, of taking a base image and writing only the blocks necessary to turn it into a derived image, is a pretty attractive option. So the last major category of analyses that I'm going to talk about today has to do with preloading. So as I mentioned earlier in the talk, at the time when a user comes and requests and asks us to provision a physical or virtual machine, we need to actually get the bits onto the disk before we can start booting it. So in order to make things go faster for users, it's beneficial to be able to satisfy their request with an image, with a disk that's already loaded with the image that they wanted. So the first thing that we look at here is relating the size of the facility and the size of the working set to our kind of success at preloading. So what we ran here is a simulation, and that simulation used the actual data set from Emulab. On the x-axis, we're looking at the ratio of the free pool, which is the number of idle disks that we have that we could do preloading onto, to the number of images that we would like to preload. So think here like the working set, right? So if we can load the entire working set onto disks and have them ready for booting, then this is a win. And in this graph, we're assuming actually that we can load disks instantaneously, so we can rebalance. And then I'm gonna relax that in the next slide. So what we have off to the right side is a facility that has a lot of spare capacity. It has a lot more disks sitting idle than images that need to be loaded. And here we can do a very good job of essentially preloading most or all of, and this I should mention also, this graph is specifically looking at the facility images, not the user images. We can essentially preload the facility images onto disks that are just sitting idle, and we can satisfy almost all user requests from that set. And if we look at the left side, we have a facility that's mostly full that doesn't have a whole lot of idle capacity. Remember again that working set size especially for facility images is going to max out on very large facilities. So the number of disks the number of images that we want to preload is going to be bounded, and the absolute number of actual physical disks that we have idle in a very large facility is probably going to be larger than that number of images that we want to preload. So in designing a disk imaging system, a critical thing to look at is this ratio of the working set size for a particular day to the idle capacity of the facility. And preloading is going to be most effective when that ratio is high. So now we looked at another key factor that affects how effective preloading can be. And so now we're assuming that disk loads don't happen instantaneously, and we're assuming that there's some rate at which we can sustain loads. So if somebody comes and asks for one of the images that is particularly popular, and we need to now rebalance things and load another disk with that image to be ready for the next request, that's what this graph is going to look at. So on the x-axis, we have the rate at which the facility can reload disks normalized to the mean arrival rate of new requests. So what we have on the right-hand side of the graph is a facility that can load disk images much, much faster than requests come in, and the left-hand side of the graph, one that cannot. And we see this very dramatic spike right around the ability where you can load requests much faster than they come in. And this suggests that if you want preloading to be an effective tactic, that a critical thing to do here is to invest in imaging that is fast and scalable, and kind of techniques of interest here include multicasting of images, broadcasting, and or distributing lots of disk imaging servers throughout the network. So I'm going to wrap up with a couple of conclusions with an eye towards the operations of data centers and areas for future research in the design of disk imaging systems. So our general conclusions here are that deduplicating multi-tier storage is quite attractive because we have a large number of disk images, especially user images that aren't used in a particular day, and we can store those in slower storage and cache the daily working set in a smaller, faster storage system. And we found that treating treating user and facility images different makes a lot of sense, especially for preloading, because the distributions of their popularity and their growth as the scale of facility grows look quite different. And then lastly, I didn't have a lot of time to get into this, so there's in this talk, but there's more detail of it in the paper, where if you're going to do that differential loading that I mentioned, it requires some very complex strategies for predicting future requests, because now you're looking not only at the popularity of particular images, but the popularity of the images that are derived from them and their similarities to those images, et cetera. So it's a complex optimization problem that probably needs some work to be effectively employed. And there's a number of other things that we talk about in the paper that I haven't covered in this talk. And so I'd invite you to take a look at it or ask me about it in the questions section. And I'd like to finish by putting up this URL. So at this URL, you can find an anonymized version of our data set. And actually, if you follow the URL, what you get is not just the data set, you actually get a virtual machine that boots up on our hardware and contains this data set and all the scripts that we use to generate all the graphs and analyses for the paper. It takes about 5 minutes, so if you start now, you might be able to finish it by the time I'm finished answering questions. This is a facility that we're actually making available to people that runs on top of Emulab for sharing research artifacts, including research artifacts that require an entire network to run on. And this is a facility that we're just starting to bring up, so if you're interested in using it to make your own artifacts available, come talk to me at some point. And thank you, and with that, I'll take questions.
Hey, Vyas from CMU. So I have a question. So people have studied this in like the video context, like whatever YouTube recommends on the homepage suddenly becomes popular. I'm sure there's like a similar effect in Emulab and EC2, where the images that are recommended or like put on like standard images are the ones that become popular. So you may actually have an option of like tweaking the popularity such that people actually use the images that you already have pre-cached by popularizing them on your homepage.
Yeah,
which
so
is
in
probably
this
already happening.
Yeah, so in this case, one thing that I didn't mention in the talk. So Emulab has a default image, which is if you don't ask for anything, this is the one you get. And in fact, this one in Emulab sucks because it's really old. And we found that even with that default, right, that, in fact, here, let's see, I can show you these numbers. So this is a table from the paper. As you can see, and here we've actually broken out how many people just took the default versus like explicitly asked for that. So the top line there is, is showing that basically only 8% of people actually just took what our default was. And in part that's because our default sucks. I think in part it's because people the way that people learn these things, they don't come to a page that kind of suggests one. They come to a big list. So we might be able to influence disk imaging, usage of disk images. I'm not particularly sure that I would want to, but
might make your management easier if everybody's using the same image, right?
No, yeah, fair enough. Yeah.
Hi, Peter, Microsoft Cloud. And I'm more of a network guy, not a storage guy, so I don't know if this is a good question. But I'd imagine the amount of disk space you have on a server relative to the amount of blocks that actually have data that's not zero, probably a lot of free space. Could you pack more images onto a server, and then when you, that way you can have less servers that you need to have available free to get more images and just zero it out and make it look like it?
Yeah, so in fact, what Emulab actually does ourselves is we actually preload we partition the disk in half and preload 2 images for kind of exactly that reason, and also for some reasons that are very specific to Emulab in terms of certain types of infrastructure nodes use certain images, et cetera. But yeah, that's absolutely an option. The thing that happens then is that, and especially if you're using virtual machines and you're going to have a whole bunch of tenants residing on the same physical disks, right? You absolutely could, give different volumes or partitions on those disks, different preloaded images. Yeah, sure.
So I have a quick question. So if you had to design now from scratch an experiment as a service system now, would you change at all the interface? For instance, would you still allow users to have their own disk images? Would you do something else?
Yeah. So so the question was, if I design this again, would I still have users having their own disk images, et cetera? And yeah, absolutely. So we've tried various strategies for kind of letting users package up specific package up their software in other ways, and essentially nobody used them. And what we found is just that as people logging to a machine, typing a bunch of commands, and saying, "Yep, that's what I want," right? And that's it's a model that people find very similar or very familiar. So yeah, I would absolutely use this same model again.